Your essential question for today is, how do we determine transformations of the parent functions? Now, there are 6 parent functions that we're going to talk about for today's lesson. All a transformation is when you move that function around, like move it up or down, left and right, reflect it, all those types of transformations. It's a really short and simple lesson, but as long as you catch up on the pattern, you'll be good to go. So, here are my 6 basic parent functions, and some of these guys you already know. In the top left-hand corner, one of the first functions y'all talked about in 8th grade and 9th grade was what we call a linear function. So this is what a linear function looks like. It makes a line, and so that's the shape of my linear function. The basic parent function of that is simply x. So whenever you see just a singular x, then that means it's my linear function. Now, we could obviously move this up or down. We could do different things to that, and that's what we're going to do to that function later. The next function y'all talked about probably in 10th grade was something called the quadratic function, and its shape was always a U shape or parabola. Its function looks like this, x squared. And so anytime you saw a function that had x squared in it, you know it's got to be a quadratic. One that we covered in this class is something called a cubic. We never called it a cubic, but it's whenever you have a degree of 3. So for example, x to the 3rd. That's my basic parent function. It's called the cubic. And here's what its shape looks like. It kind of looks like a weird S, but it's basically this shape right there. Now again, we're going to take all 6 of these shapes and we're going to move them around, like move them left, right, up or down, stuff like that. All right. One that you probably covered in 9th grade but never actually graphed is this top right one. It's called the absolute value. The reason why it's called the absolute value is because it's inside those absolute value symbols. So that's called the absolute value function. And its parent function is just simply the absolute value of x. The way I remember what the graph looks like is check out the word. You see where it says absolute value? What letter do you see right there in there? A V. So that's why I knew it was going to make a V shape. Not the most mathematical way of remembering something, but it's the way I remember it. The next shape, something you covered in 9th grade, was something called the square root. Y'all know about the square root, but you probably never graphed it. You might have, maybe not. But here's what the graph looks like. It looks like this shape right here. Well, if you're probably wondering, well, why the heck isn't there any picture over here on the left-hand side? Think about that for a second. What type of numbers are over here on the left-hand side? Negative. And can you take the square root of a negative number? No, not with it being anything but imaginary, right? So these are non-real numbers on the left-hand side. So the square root of x looks like that picture right there. And then one that you probably have not covered yet is the function 1 over x. That's what we call a rational. And while I'm here, teachable moment, guys, the words rational in math, that basically means a fraction. So you've got 1 over x, that's a fraction, so that's a rational function. We're actually going to spend one day just covering rational functions. Not now, but a little bit later on everything we can do with rational functions. But here's the shape of it. It's the one that's a little bit different than any other one because it has something called asymptotes. And I'm going to show them to you on this in a second. If you notice, there's the graph right here. It's this shape and this shape. Something that you probably remember from 9th grade about what the definition of an asymptote is. It's a line where your function gets closer and closer and closer to, but it never actually does what? Does anybody remember that? Touches. That's right, yeah. So, for example, the rational function is the only one. Well, I don't know if I can draw it in here. It has 2 asymptotes. It has one on the y-axis, and it has one on the x-axis. You can't really see it because it blocks out from there. But it does have 2 asymptotes, one at the y-axis and one at the x-axis. And so then there's the shape of my rational function. Now, guys, you don't need to know all this domain and range and end behavior, even though that's good to have right there. You don't need that. All that you need to make sure you've got are your 6 parent functions. So what I'm going to do so you can see it better, I'm going to go ahead and take a second, and I'm just going to redraw them right here, right quick, and go through the spiel one more time. So this is the main thing you've got to get from it, is that your first function is your linear function, and all it is a straight line. Your next function is a quadratic, and that is a U shape, so it looks like that. The next one is a cubic, so x cubed, and that looks like this. The next one is your absolute value, and it looks like the V, so there's my absolute value. The next one is your square root function, and it looks like this. And then the last one is your rational function, 1 over x, and it looks like this. It's the only one, and I can show it to you better now, it's the only one of my 6 functions that has 2 asymptotes, one at the x-axis and one at the y-axis. But that's it. Now, what we're going to do is we're going to take these functions and we're going to transform them. You're going to move them. You can either move them up or down, left or right, or you can reflect them, all those interesting things. And it's really simple as long as you pick up on the pattern. Once you've got the pattern, you're good to go, and you can do these really, really quickly. All right, I'm going to pause. All right, so let's jump into this, and then let's take a look at some examples of this in action. So let's talk about vertical translations. So that's if you're taking a function and you're moving it up or down. So let's start off with something very simple. All right, this is the quadratic function, right? X squared. And you notice its parent function is drawn, it starts at 0. Well, just take a guess. What do you think would happen if you took that function and simply added 1? What do you think would happen to the function? Your instincts are right. Anytime you take a function and you add a number to it, it moves that function up. Does it retain its same shape? Yeah. So if you had that function and you subtract 3, then what would happen to that function? The only thing would happen, that's right, it would just go down 3. Does it retain its shape? Yeah. Now, here's one thing that's not mathematical. That number, is it on the inside or the outside of the function? It's on the outside. So anytime you have a number on the outside of the function, it moves the graph either up or down. That's it. So, for example, if you have the absolute value function, you see how the absolute value symbols are there? What I mean by inside versus outside, if the number was inside the absolute value symbols, then that would be inside. But if it's on the outside, it's not inside those absolute value signs. So, for example, if I gave you that function plus 2, then that graph would simply move up 2, shift up 2, still retain its same shape. If you had f of x minus 4, so you had that function minus 4, it would still retain its shape, and it would just go down 4. So anytime you add or subtract a number to your function, it's going to move the graph up or down. All right, now, here's where it's different. Let's talk about horizontal translations, moving your graph left and right. Now, let's say that you took your function, and you see where I put this x plus 2? Is that inside or outside the function? It's inside. But remember, think opposite. So if that's a plus 2, which way do you think I'm going to move the graph? To the left. And that's exactly what happens. See in red, that function moves to the left. So if you have your regular x squared graph and you do x plus 2 squared, it's going to move that graph to the left 2 places. If I had x minus 1 and it's inside the parentheses, you would literally take that function and move it to the right 1. So in green, anytime you add or subtract a number on the inside of the function, it moves it left or right. But always think the opposite. That's what's key for that one. Another example, your cubic function. So there's my cubic function. If I were to tell you to take that function and do plus 1 on the inside, then it would simply move that shape to the left 1. If you had f of x minus 3 inside the function, then you would simply take that shape in green and move it to the right 3. So anytime you have it inside the function, always do the opposite, and it moves left or right. And we're going to go over all those rules again at the very end. All right, now let's actually do them both together. Let's say you had your square root function. So let's just say you had the square root of x. What do you think the graph would look like if I gave you this on the test? X plus 2 plus 3. What do you think would change to this function that's in blue? Where would it go? It would go left 2 and up 3. And so if you went left 2 in green and then you went up 3 in pink, then that in pink would be my final answer. That would be the translation, the transformation from blue to pink. That would be my final answer. All right, now let's talk about stretching versus compression. Stretching is when your graph gets closer to the y-axis, if you can see that. Compressing is when your graph gets closer to the x-axis. So it's kind of like getting narrower and it's getting wider. So stretching versus compressing. Now, here's how you tell whether or not your function has either stretched or compressed. It's all about what you multiply the function by. So let's look at some examples. Let's say you have your absolute value function, just your basic absolute value function. Let's say that if I told you to multiply that function by 2. What happens when you multiply by a whole number? It makes the graph get narrower. Do you see in red how it's getting closer to the y-axis, and it's actually getting narrower versus the blue. So in red, that's how the new function is different. If I were to multiply it by an even bigger number, let's say 4 times your function, look in green. It gets even closer to the y-axis, so it gets more narrower. So anytime you multiply by a whole number, it gets more narrower. And so that's what happens with the stretches. Now, let's say you take the same thing, same absolute value function, but this time instead of multiplying it by a whole number, it multiplies it by a fraction. What do you think is going to happen to the graph this time? Is it going to get close to the y-axis or to the x-axis? X, that's right. So take a look at this in red. If you multiply that function by 1/2, look in red, it's actually compressed. If you multiply it by 1/4, it even gets more compressed in green. And so that would be what your shape would look like. So multiplying changes either compression or stretching depending on if you multiply it by a whole number or a fraction that's between 0 and 1. It's got to be between 0 and 1. All right, and so that's the examples for that. All right, now, here's what's interesting. Let's say you take the absolute value function, and let's say you multiply it by a negative number. So let's say you put a negative in front of your function. If you have a -1 in front of your function, what happens is it reflects it across the x-axis. So you see in blue, that's my absolute value function. But if I ask you to graph negative absolute value of x, look in red, all it did was flip the shape across the x-axis. It just reflected it across that point, and so that would be my reflection. Now, what's interesting is if you multiply it by a negative inside the function, it doesn't reflect it across the x-axis, it reflects it across the y-axis. So if you look for this one in blue, your cubic function, you see in blue, if you have a negative inside the function, you see that negative x cubed, it doesn't reflect it across the x-axis, even though it looks like it, it reflects it across the y-axis. And so in red, that would be that new graph for that one as well. All right, I think we're going to tie all of this together right quick. So take a second, and what I would probably do is write down this function right here.